This is a conversation with Lawrence Krauss. He's a theoretical physicist, cosmologist, and the best-selling author of multiple books, including The Physics of Star Trek and A Universe from Nothing. He's the president of the Origins Foundation and the host of the Origins podcast. In this conversation, we discuss the role of beauty in physics. We talk about the state of the union for physics, for experimental physics and theoretical physics. And then we talk about the origins of the universe, the Big Bang, what was there before the Big Bang, how the universe emerged from nothing. And we also talk about light topics like dark matter, dark energy, and God. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars on Apple Podcasts. This project takes a lot of my time, money, and effort. It's almost like a second job. So if you'd like to see it continue, do consider making a donation on Patreon or Anchor. You can leave a gift on Instagram. You can buy super thanks on YouTube, or you can join and become a member on YouTube. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. On a dark and stormy night in 1917, Einstein discovered that the planet Mercury deviated from its orbit by 1/100th of a degree. And when he used his theory of general relativity to confirm that number, he was reported to have heart palpitations, like something snapped inside. A month later, he would describe his theory as one of incomparable beauty. I want to start there. When was the first time in your life when you had a similar reaction to physics or math? Do you vividly remember a moment when you had heart palpitations from just an idea or a discovery?
Yeah, most often they were wrong though. I remember when I was a little kid, actually, not that little, but I remember figuring out once about that if particles were waves, I could kind of derive what were the Bohr orbitals, which at the time, 60 or 50 years earlier, someone won a Nobel Prize for, but I was thrilled to see that I got that right. There have been a few times when I had the solution to a problem, once related to something called the solar neutrino problem, and I suddenly realized that dark matter particles could be captured in the sun, maybe, and they might solve the problem. It seemed like it was a way to solve two big problems in astrophysics. I was very excited about it. It turned out I proved a few days later that it didn't work. Other people talked about it for a long time and wrote it up, but it doesn't work. But probably for me, very few people get to do what Einstein did. So I suppose very few of us have the heart palpitations that he had when he realized something wonderful. But I think when I heard that. When I first heard the results that two observational groups had discovered that the universe was accelerating, which validated an idea that we had proposed 3 years earlier, that the universe was full of dark energy. I don't think it was heart palpitations. It was shock, I think. Absolute shock that we were right. And because I wasn't convinced we were right. It was kind of a heretical proposal, but everything seemed to point at it, and no one believed it at the time we said it. I can tell you that. And then to discover we were right was a shocking thing. It's really amazing if you're a physicist, and I can understand how Einstein felt in this sense. And I've talked to several other physicists, some of them have won Nobel Prizes. It's very intimidating to think that something that you're working on, maybe late at night or on a piece of paper, that the universe actually might obey it, about that idea, especially since, frankly, if you're a scientist, a theoretical physicist, more often than not, you're wrong in the sense that you have ideas that are not wrong, the mathematics is right, but nature doesn't decide to utilize it. And so it is really a shock when it's right. It happens every now and then, and not very often, but it's kind of neat when it does. And I'm lucky in my life that major shock happened, and it was such a big shock that was later awarded the Nobel Prize. So it was a big shock.
In those few instances when it did happen to you, like Einstein, did you ever consider your theory to be of incomparable beauty? And while we're there, what role does beauty play in science? I say that because there are many theories out there that propose that nature is inherently beautiful. There's a belief in supersymmetry, the design argument that says that nature is intrinsically symmetrical, beautiful, elegant, simple. What role, or is it fair to assign some weight to theories that have like that assume that nature is inherently beautiful, or that's just a nice to have?
I don't think so, really. I think, first of all, most theories are beautiful in the eye of the beholder. I have many colleagues. Most physicists I know think their own pet theories are beautiful, but most of them are. But very few of their colleagues think so. I have had one or two theories that I've written down with colleagues about to try and explain things that seemed at the time to be beautiful for me, and it just happened that nature didn't obey those things. But if namely the phenomena that we were trying to explain in several cases went away. But if it had been real, there was only one way to explain it, and it was our beautiful idea. It wasn't real. But I think beauty is overrated. I really do. I think after the fact, we can understand mathematical beauty, I think. But it's hard to know what makes physics ideas compelling to the theorists who develop them. I think most often it's kind of an accident. We're sort of driven, sometimes kicking and screaming, and afterwards we can see the beauty. But many times we don't really understand that when we're actually working on it. It's only after the fact. I mean, James Clerk Maxwell's equations are beautiful. For 4 equations that describe everything we see: light, electromagnetism, but they weren't so beautiful, I think, when or at least, I don't think they were so beautiful when Maxwell first developed them. And similarly, there's a mathematical symmetry that governs all the known forces in nature. And again, I think it's kind of after the fact that we realize the mathematical beauty of it. So I think there's far too much talk about beauty. I don't think what really matters in physics is whether it agrees with experiment. And then we find a reason to find it beautiful after the fact. But elegant, beautiful. If it doesn't agree with the experiment, we throw it out like yesterday's newspaper. And so it doesn't, I think all these talks about beauty are often misplaced, because once again, I don't think there's an objective. There are mathematically attractive formalisms, but it's hard to know about an objective criteria for beauty. Once again, it's like someone you fall in love with. After the fact, you realize there's something beautiful sometimes.
Okay, so you brought up some talks in physics that are misplaced. Let me ask you one more question about your journey. During your undergrad, you actively took up courses in maths because you wanted to avoid spending time in a physics lab. You felt that spending 6 months of your time tuning up a cloud chamber is probably not the most exciting use of your time. And you found theoretical physics to be more exciting at that point. I want to get your thoughts on the current state of physics. If you had to create like a state of union for physics at the moment, for someone who's just coming in, how do you view, I guess, both experimental physics and theoretical physics? There are some people who would say that theoretical physics, at least a certain subsection of it, is now stagnated or at a standstill because of string theory. So how would you create this pulse or this sentiment around theoretical physics and experimental physics?
Well, first of all, the older I got and the more knowledge I got as a physicist, the more I appreciated experiments. Younger, I didn't. I spent time in a lab, working in a lab as an undergraduate, and I found it very frustrating. But it was also seemed so much more sexy to the mathematics and developing new ideas and following the footsteps of Einstein and Feynman. But physics is an experimental science, and I'm often envious of my experimental colleagues, because once they've done an experiment, they have something tangible. If you're a theorist, it's very hard. You don't have very many tangible things. It's sometimes even hard to call an idea your own, because often many people have similar ideas. And so it's not as satisfying, I think, as having done an experiment. It's like building anything, right? I mean, you build something and you can see it. Well, you build an idea and it's maybe attractive inside, but there's not an objective evidence that it's there or that it's yours, let's say. I think, people hype things too much. String theory was hyped too much, but the doldrums are probably hyped too much. Physics, look, if there was a new wonderful result every year, it wouldn't even be exciting in some sense. So yeah, there's a lot of puzzles. We are at a point where there are some major fundamental puzzles in theoretical physics. And it may take 100 years to solve some of them. I'd hoped that experiments would maybe discover supersymmetry, evidence for dark matter, some kind of evidence for that would give us something to go on beyond the standard model, why the Higgs is where it is. So there are a lot of mysteries, and some of them may be pretty hard to solve. I think there are many, but that's just one area of physics. There's a lot of areas of physics where there's incredible excitement. And generally, whenever we open a new window on the universe, a new experimental window on the universe, physics gets exciting. And so, in fact, what you saw when the Large Hadron Collider developed, you saw a lot of string theorists jump ship like rats. Because, hey, suddenly there was going to be experimental data and maybe it might reveal something new. And so I think, we're building new telescopes and they're going to reveal new things. We have new technologies for handling quantum phenomena, maybe at a macroscopic scale, and being able to manipulate materials in new ways. So there's lots of exciting new areas of experimental study and even biology, experimental physics as applied to biology. So I think that rumors of the demise of physics are incorrect. Absolutely, and I think theory is fascinating because there's two ways of doing theory, and I've done both in my life. Mm-hmm. You can come up with theories that experimentalists try and prove. Experimentalists try and disprove them. Let me make that quite clear. And they love disproving theories. I've had many theories when experimentalists say, "Oh, we disproved it." They're so excited. But so you can that's one kind of theoretical physics. But the other is to explain experimental results that are perplexing. And that's what led us to the idea of dark energy initially. There were many experimental results that were perplexing, and we realized it could all fit together in this one picture. And so, even if coming up with fundamental theories may seem daunting or may have been difficult because of a lack of maybe data for a long time, once new things turn on, it's exciting for both theorists and experimentalists. So. Would I become an experimentalist now? Well, I would maybe, except I'd have to have a whole different skill set than I have. It's a little late now, but I certainly appreciate it. And one of the things that I'm giving you a long answer, but it is my answer. I originally, as you kind of pointed out, I originally did mathematics and physics. And then when I entered graduate school, I did mathematical physics. I did what you might call mathematical physics. Mm-hmm. It was very, very formal. And it was a now friend of mine, then a mentor, and a guy named Sheldon Glashow, who won the Nobel Prize in Physics, yep. who became a very good friend. When I was a graduate student, at one point, he said to me, "There's physics and there's formalism, and you have to know the difference." And it was in the process of that I realized that I never really wanted to do things that were not in touch with experiment in one way or another. And that was a significant decision for me. And that meant I had to learn what was happening experimentally. And I find that very satisfying. So I've always in my career liked to be in touch with what's happening experimentally, or even develop new experimental techniques. Even though I'm not an experimentalist, I've been involved many times in proposing new ways to detect things. We proposed new ways to detect dark matter 40 years ago, and I thought in 4 or 5 years the experimentalists would have done it. It takes them a lot longer, which is maybe one reason I'm happy to be a theorist, because then I can move on to other things. But anyway, so I think there's no doubt particle physics has been in a difficult situation. There hasn't been a new discovery that surprised us, perhaps, except for neutrino masses, and even those were kind of expected in some ways. But something that led us in a new direction in 40 years, and that's very difficult. And that means that sort of fundamental theory in particle physics is problematic right now. But you never know when the next good idea is going to come along. And that's why I turn to sometimes the universe, because the universe can reveal fascinating things. The universe, after all, is a particle physics experiment. Done at least once. It was done once at the Big Bang, and now it's data analysis.
The universe can reveal a lot of fascinating things. You mentioned, well, first you mentioned a theory that gave you heart palpitations was the theory of the universe emerging from nothing. And then you also spoke about dark matter, dark energy. Let's start the heavy lifting now. Let's start talking about these theories. But before we go there, just to set the context for someone who doesn't know, first let's just quickly talk about the Big Bang and how we got here. So what was the Big Bang and how do we go from the Big Bang to the world that we know today?
Well, we don't know what happened at t equals 0, so we don't have laws of physics. But a little bit later, we do know because we can measure our universe, and we can even measure remnant phenomena going back to maybe when the universe was a millionth of a second old. And the Big Bang was the fact that all of space was expanding and filled with a hot, dense soup of radiation and cooled down. And we can trace back, evidence of the universe back to when it was 10 billion degrees, maybe 100 billion degrees, maybe a trillion degrees. That's like a millionth of a second after the Big Bang. And then we can make predictions based on the laws of physics, and we compare them with observations, and they all agree. Those predictions tell us that the Big Bang really happened. So the universe, our visible universe, was contained in a very, very small region. It's hard to region smaller than the size of an atom. It's hard to imagine all of the energy in 100 billion galaxies, each containing 100 billion stars, in that kind of region. But in fact, there was even more energy because a lot of it has dissipated as matter and energy have done work on the universe as it's expanded. So, but it wasn't from a single. It wasn't as if all the space came from some single point that I could point to. Space was expanding everywhere. So there was no center of that. All of space was expanding, and everywhere has been expanding since. So there's no center of the Big Bang. Yeah, that's a hard thing for people to picture, but it is true nevertheless.
Everything from t+1 adds up. That makes sense to me. T equal to 0, maybe it's a point of singularity. We won't go there. But
we need new physics to discuss it. And I postulated what might have happened, and you know about the universe from nothing, but that's what might be plausible, but we don't have a theory yet.
Okay, let's go to it. Let's go to t-1. Let's go to.
Well, let me make it quite clear. T-1 might not exist. It's very important to realize that space and time may have come into existence when the universe came into existence. There was no, in that case, there's no before. There's literally no before, and it changes what way we talk, because we usually think of cause and effect and everything else. But if space and time began when our universe began, there literally, at least in our universe, there was no before. Now, our universe could have arisen and been embedded in some other object, some space that was pre-existing maybe, but our universe, literally, our space and time didn't exist. And so as far as our universe is concerned, there was no T, but more likely there was no before. Just so you know, no P-1.
Yeah, let's linger on this a bit more. When you say the universe emerged from nothing, what does that mean? How can we even think of it? What does nothing mean in this context?
Well, I mean, there's lots of, I wrote a whole book about it, right? But yeah. I think the key point is, the most important version is that if space and time are quantum mechanical, if gravity is a quantum mechanical theory, then space and time are quantum objects, and quantum objects fluctuate. And so you can imagine literally a closed universe that did not exist, that suddenly pops into existence. That space wasn't there. It wasn't there, and suddenly it's there. And then, of course, most of such spaces will collapse instantaneously and disappear. But every now and then, one such space could pop into existence by the laws of quantum mechanics, so space and time could suddenly arise, a closed universe. It could expand exponentially fast by something called inflation, and it could end up looking like our universe. And if you wanted to ask what would a universe look like that went through such a procedure, it would look identical to the universe in which we live. That doesn't prove that's the case, but it makes it plausible. So when I talk about nothing in there, I mean no space, no time, no particles, no radiation. Nothing that is part of our universe now existed but until it came into existence. Now, whether there's something else in existence, something grander and broader, and whether there's a multiversal time where you can label when our universe came to existence, all of that is speculation and kind of irrelevant for understanding our universe.
Okay.
I know it's hard to conceive of these things. Believe me, I understand that.
How much of our current world is dependent on the origins? Can you can we treat the world that we live in today as part of a Markov chain, in the sense that how I got here today is independent of any historical states? Or do you think the fact that the universe emerged from nothing has some form of a profound implication on how I view the world today and would change my perspective and the science?
I think, well, yes, in a general sense, we how we got here changes our perspective of ourselves and our place in the universe. It's not going to make a better toaster or a faster car, but I think what it does do is point out something that I think is highly non-intuitive, and one of the reasons we have religions is that we live in this universe, as I said, that has hundreds of billions of stars, and 100 billion stars in our galaxy alone, and 100 billion galaxies or more in the visible universe. In order to, it certainly feels like in order for all that to come about, something had to create it. There had to be something there. And what is remarkable is that it can be the ultimate free lunch. It all can come from nothing, and you don't need any supernatural creator, or anything beyond our universe for that to happen in principle. And that's a remarkable result, and a remarkably freeing result, because requiring something to create our universe, then it just throws the questions back. Who created the creator, and what did that? I mean, it doesn't answer anything. And so I think it changes our perspective of meaning and purpose, because if the universe spontaneously arose, there's a quantum fluctuation, there is no meaning or purpose to the universe. And that's okay. We make our own meaning and purpose. Some people may find that disappointing, but the universe doesn't exist, so you can be happy.
You brought up the meaning and purpose. Let's park that question. I am going to ask you that, let's say 15 minutes from now. But you also brought up the creator. Let's go to that one first. So Einstein had once asked the question, what I want to know is whether God had any choice in the creation of the universe. Now, Albert Einstein is not here with us today to ask that question. So I'm going to channel him and ask you the same question. I want to know whether God had any choice in the creation of the universe. But when I say that, I'm going to concede that there are multiple theories about a creator. There's the Spinoza's God.
Einstein, one thing is for certain, Einstein never meant God when he said God. Okay, he never meant the God that anyone normally talks about. I mean, it was his way of just talking the old man, what he really meant by that statement. He framed it in a poetic way, but he's not there for me to confirm this, but I can assure you I'm channeling him now. He meant, is there a unique law of physics? Are the laws unique? Namely, if I tweak some knob and some force different, would all of reality disappear? Is there only one way to put together a consistent reality, and can we explain why the universe has to be the way it is? That's really what he meant. And that is the question that's of most interest to me. And unfortunately, and I say it unfortunately because I became a physicist, like many people of my generation, to try and explain why the universe was the way it was and couldn't be any other way. That's what excited me. I think it's probably misplaced, that in fact our current picture is that it may just be a big accident, that the laws are what they are, without any fundamental necessity for there to be four forces that have we can try and understand why they are that way within our universe, what set of phenomena, when I say why, I mean how, what caused that to result. But there could be many universes in which the laws of physics are quite different. And, if that's the case, then unfortunately the answer to Einstein's question is that God, namely non-God, had lots of choices. And that even makes, and what makes that interesting perhaps is it even further removes the need for God at all, right? If there's lots of different universes that can be created, you don't need some intelligence to create one. You just need to be fortunate enough to live in one in which life can evolve, and then ask these questions.
Right. Okay. Let me try to channel the people. We try to channel Einstein. We changed that. Let me try to channel the people who like to believe in a theory of a creator. There are multiple theories. So there's one about the divine creator, of course. There's Spinoza's God. There's the simulation hypothesis, that the universe is nothing but a simulation in the lab of a...
Equally silly. Mm-hmm.
And then obviously there's a theory that there is no God.
I don't know. There's no theory that there is no God. It's just it's like saying we have a theory there are no unicorns. I mean, it's just, do you believe, is there any evidence for unicorns? No. Is there any evidence for God? No. Spinoza's God is just, all he's saying is, and it is awesome, that there's order in the universe, the fact that we can understand and explain the universe is amazing. And the fact we can do it with mathematics is even more amazing. And that awed Einstein, and it awes every theoretical physicist. It's amazing that we can, in succinct form, write on a single piece of paper a set of equations that describe almost essentially everything, describe and explain and predict basically everything we see in nature. That is shocking. Why it's the case is amazing and awe-inspiring. And you can call that order God if you want. And I think that's what Einstein meant. The simulation hypothesis is just another example of kicking the can down the road. I don't understand why it interests people, because first of all, there's no evidence that we live in a simulation. Usually simulations have pixels that don't work, as far as I can tell, except perhaps in the mind of the ex-president of the United States. Things work. But more than that, you say, oh, we live in a simulation. Well, that must mean we're created by something more complex than us, right? Well, who created them? Are they a simulation and another simulation? Is it turtles all the way down? And if it isn't, you're telling me that an incredibly much more complex organism could arise naturally, and somehow that, because it seems impossible that we could arise naturally. I mean, it doesn't make any sense. If you really try and parse that idea carefully, I think it doesn't make sense. And at least it's not compelling. It's not that it doesn't make sense, it's possible. But it doesn't answer any questions, does it? It doesn't explain, it doesn't help you with the laws of physics. And even if we were in a simulation, I don't give a damn. I want to know how the laws in our simulation work. That's all I care about. Because there are laws. I throw up a ball and it comes back down, and I can explain it. Gravity, curved space in the simulation. So I want to understand what governs the way our universe works. I see no evidence it's a simulation. I think the idea is silly, but even if it is, I don't give a damn. I'm not I like physics, not metaphysics.
We just spoke about the profound implication of considering your origins and how that changes your perspective in life. If it were a simulation, then just accepting that idea would get us closer towards now identifying what's more fundamental.
Why? It just says, no, it's just saying, blah, 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 I can't figure it out. So something else that whoever created us figured it out. I mean, why does it get us closer? It gets us farther away than to try and understand how the universe works, because you're passing the buck onto some intelligent entity that decided for some reason to create a simulation that may or may not reflect the world in which they live. So I think it does the exact opposite. I think it, just like religion, you talk about a simulation, it means you stop thinking. Religion, when you mention God, okay, I don't want to think anymore. I'll just call it God. Don't want to think about it. Don't want to try and understand it. Call it God. It's lazy thinking.
We've been channeling a lot of people. I feel like you've been channeling Christopher Hitchens here, using his razor.
He would be very disappointed to think I've been channeling him, because he's so much more eloquent than I am. He was, anyway.
But you have been at least dismissing things that have been asserted without evidence.
That's right. And exactly, as he said, yeah, exactly.
So you spoke about working in physics and not metaphysics. Let me channel someone who's actually an influence to you early on in your life. I'm going to quote Sir James Jeans from the book, The Mysterious Universe.
Oh, wow. Okay.
He had said the following words: "The stream of knowledge is heading towards a non-mechanical reality. The universe begins to look more like a great thought than like a machine. Mind no longer appears to be an accidental intruder into the realm of matter. We ought rather hail it as the creator and governor of the realm of matter." Is there room for James Jeans' idealism in your theory of the origins of the universe? He had
no, and he influenced me a lot. His book Physics and Philosophy influenced me a lot when I was a high school student. But what it did was cause me to think more that philosophy was more interesting than it is. I think, but there's a lot. It's a wonderful book, but there's a lot. It was written in 1930, and the world has changed in the last 100 years, almost 100 years. So it's quaint. I wrote in my new book, The Edge of Knowledge, which, by the way, was motivated, as I think you may know, by the mysterious universe. And I have the same thought. I wonder how many of the things I write now will seem quaint and out of date 100 years from now. I hope a lot, but I don't see any. His notion that somehow mind plays a special role. I find everything I know about the universe suggests the opposite. That it's a wonderful, remarkable accident that we are conscious, and maybe one day we'll create other consciousnesses through our machines. But the universe exists very well without us. Thank you very much. I mean, we go out of existence, and the universe is largely the same. So I don't see that in any way mind plays a special role. It's the opposite of what Deepak Chopra might think, who thinks that everything has a consciousness, including electrons and candy bars, as far as I know. Anyway.
So you're bringing an aspect of realism into the universe. It's saying that the observer is not that important, and there is something that's mind independent.
Of course it is. The star that exploded, the supernova that exploded to create the elements that made you and I up, and to compress the materials that would eventually lead the gas cloud to 4.5 billion years ago to collapse to be our sun and our solar system. That was all fine without anyone observing it, and happily so, because we wouldn't be here if it required us to be here to observe it in the first place.
Okay.
I think people. Quantum mechanics makes the observer, quote unquote, makes the observer seem important, and people think the observer is akin to a conscious observer, but that's the observer. There's lots of observations. Observations can be made with Geiger counters, right? And they're not very conscious. I have a Geiger counter here, and it's never talked to me.
Until now.
Maybe in future AI Geiger counters will exist that will talk to me, but even those I'll be suspicious of.
Yeah, who knows? Maybe that will change. Okay, you also brought up dark energy, so I definitely want to cover that. What is dark energy? Why is it such a mystery today?
Well, dark energy says that empty space has energy. Empty space weighs something. There's nothing there, but it has energy. So don't you think that's pretty mysterious?
Yeah.
Well, it is mysterious when you say it, but it's more mysterious. But you have to know a little bit more to realize how mysterious it is, because it turns out once you allow for quantum mechanics, it's not too surprising that empty space could have energy. The quantum systems always have what's called a ground state energy, and it's often non-zero. But what's really surprising is that the universe has empty space has energy, but it's so small. It happens to be the dominant energy in the universe, but the energy of empty space is less than 1/1,000,000th of the. So in our galaxy, the average density of matter is 1 proton per cubic centimeter, and in empty space it's 1 proton per cubic meter.
Mm-hmm.
And the energy of empty space is much less than the energy of the random amount of matter in our galaxy. Much less than it. It's so small that we never knew about it, and the only way we can measure it is by looking at the universe as a whole. We can't measure it in laboratory experiments. It's just so small we can't see it. Smaller by 30 or 40 orders of magnitude than we can measure now in a laboratory. I hate to say the word ever, because I've learned that experimentalists are smarter than you think. They just look. Anyway, no, that's a joke. Anyway, so we need to use the universe as a whole, and it's only observable on the scale of larger than clusters of galaxies, where matter is so rarefied that the energy of empty space begins to be significant. And it's well, in natural units and I'm not going to explain what those are, but in the kind of unit, if you think of the scale of particle physics, particles and their masses, the energy of empty space the energy density of empty space is anywhere between 60 and 120 orders of magnitude smaller than you might have expected based on the other scales in nature. So the big surprise is, first of all, that it's not zero, because we always thought it was zero, because that's a good number. And it also, if it was zero, then it would explain why we never saw it. And then we discovered it wasn't zero. Some of us proposed it wasn't zero, and then it was discovered it wasn't zero. But the number is so small that it's ridiculous. It's smaller than, in units of the scale that where you might think it would be, it's 10 to the minus 120. That there's no other quantity in nature that in any kind of sensible set of units is that small. And so we don't have the slightest idea why it's there, and we don't know why it has the value it has. We don't even know if it's fundamental. We don't know if it's what's called a cosmological constant, which Einstein predicted, but he didn't know why he predicted it, really. But quantum mechanics predicts a cosmological constant. Maybe it's some fundamental vacuum energy of empty space, or maybe it's just some energy in some field which is going to go away tomorrow. And there's lots of ways it could go away tomorrow. One of the ways it could go away tomorrow is there's a phase transition, and then everything I see behind you and everything, all of nature that you now see will disappear instantaneously at the speed of light, so you won't know you've been hit. Or maybe not. One of the theories I proposed, where I was very happy to save the universe, gave a way for dark energy to disappear without causing much of a ruckus. But the theory is probably wrong. But I think it's most likely that it's the energy of empty space. But we don't have yet, there's no evidence. Well, I shouldn't say there's no evidence. The big question is the energy of empty space changing? And I bet a number of people, I bet my friend Stephen Hawking and Frank Wilczek and other people about when it was first discovered, that we wouldn't know. There's no experiment that would tell us in the next decade whether the energy of empty space was fundamental or not. And even though, Stephen's died, but Frank denies he took the bet. But they did. And there's been no experiment that could tell us that. And now it turns out this last year, some new observations have given a tantalizing suggestion that maybe the energy of empty space is changing. But the experimental data is unconvincing. And also, the way it's changing seems ridiculous. So my suspicion is that like many things, the first time you look at something very difficult to detect, you get it wrong. Usually, the first time most experiments measure something, they get it wrong, especially if it's hard to measure. There's no theoretical explanation of it, and there's no experiment so far that can tell us anything about it, except that it's there. And that's pretty mysterious and frustrating at the same time.
Yeah.
I suspect we need to know something about quantum gravity before we can resolve this issue, and we don't have a theory of quantum gravity.
This difference between the observation and the expected energy of dark energy has led people to create a theory of the multiverse, where there are multiple different universes where this energy has different values. And what is now known as the Anthropic Principle, we just happen to be in the universe where the energy is of this value, but there are universes where this energy is on a spectrum and everything exists.
That, every time there's been a quantity that's inexplicable, people have come up with the anthropic argument. It's happened many times in the history of physics. And what often happens is finally we come with a fundamental theory that explains it, and people throw out the anthropic. The same may be true for dark energy, but right now it's the best explanation. And the first person who gave it in a clear form was the late Steven Weinberg, another mentor of mine in some ways, certainly one of the greatest theoretical physicists of the last half of the 20th century. And he pointed out, before it was measured, to be fair, to give him fair, that if you assume this anthropic principle, then how large could a cosmological constant be? And it turns out if it was any larger than what we measure, then the universe, then galaxies wouldn't have formed, and planets wouldn't, stars wouldn't have formed, and people wouldn't have formed. So he said, if it's a random number, maybe it might be this big, and that's about as big as it is. So, if the energy of empty space were much bigger than what we measure, we wouldn't be around to ask the question. So it could be there are many universes, and in some of them the energy of empty space is much bigger. It could be a random variable with no fundamental significance. In those universes, at least life like us doesn't exist. Maybe other life forms could exist. Weinberg's argument has to be revised, and there's certain way. And when you revise it carefully, you might say it's not as compelling as it was when he first proposed it. But it's at this point, it's one of the best. It's the only perhaps explanation, since we have no fundamental physics explanation of the energy of empty space.
So what's on the horizon? How do we, like, at what point do you think we're going to make a breakthrough?
Look, people, how do I know? I mean, people always ask me, what's the next big thing? And I always say, if I knew, I'd be doing it. All we can do is perform every experiment we can do. Measure the universe every way we can, open up every new window we can, and hope that one of them tells us something or surprises us. But who knows? What is certainly true is that the next big breakthrough will happen in those areas where we have new windows. And there are lots of areas, but where it'll come, maybe it'll come at a particle accelerator, maybe it'll come at the James Webb Space Telescope, or maybe it'll come with the next generation of gravitational wave detectors, or maybe the cosmic microwave background, or who knows. We build a lot of things, and we look at everything we can look at, and we wait for the universe to tell us how it works. It's not up to us; it's up to the universe. And some people say, well, that's just a waste of time because you're looking for things, and most of the time you don't find them. And well, that's what makes it's a struggle. It's a search. It's the mystery that makes life worth living. It's not the finding, and that's trying to puzzle our way through life it's not just a part of science. It's part of all of culture, about art and literature and music, and so it's a wonderful thing to have mysteries. It's not a depressing thing.
I'm going to park the question about mysteries aside as well. We will come back to it.
Yeah, we'll have room for all the questions you're going to find aside. Okay.
We're going to fit it all in. Don't worry.
Okay.
We spoke about the past. We spoke about t+1, t is equal to 0, t minus 1, and whether that even existed as a concept. Let's talk about the future. Let's paint a picture of the future. Maybe a million. Whoa. I don't know if you can hear the train in the background. That's New York.
I can't, but I live in a quiet, peaceful place, not where you live.
Yeah, I can always randomly hear sirens. Okay, yeah, so let's paint a picture for the universe in the future. Let's say 1 million years from now, 2 trillion years from now. What's going to happen to our galaxy and the neighboring galaxies, and how's that going to change the science for the cosmologists that are going to come in the future?
Well, as you know, I've written about it. So, 2 trillion years in the future.
Yeah.
Well, first, let's do the history starting quicker, okay? Just so people get a sense. In 2 billion years or so, the sun will be 15% hotter. When that happens, there'll be a runaway greenhouse effect on the Earth, and the surface of the Earth will become like Venus is now. So the temperature of the Earth will be maybe 600 or 1,000 degrees. Not pleasant, even if you live in Phoenix now, where I used to live.
Yeah.
Which felt like hell most of the time. Anyway, that's 2 billion years. In 5 billion years, the sun is going to use up all of its hydrogen fuel, most of it, and the core will collapse inward, causing it to start to burn helium, and the outside will expand. So the sun will become larger than the Earth's sun orbit right now. So the Earth will be inside the sun unless we move the Earth, which we could do. So the Earth will be toast, okay, and everything that you now see will be gone. Well, it'll be vaporized and out in the cosmos. That's only 5 billion years, though. That's not much. Stars will last in our galaxy probably as much as 10 trillion years. The longest lived stars. And what'll happen is that before that, in about 5 billion years, the Andromeda galaxy is going to collide with our own. Won't cause much damage, except the galaxy will change. Very few stars will hit because most of it's empty space, but we'll stop being a spiral galaxy and will become kind of an elliptical galaxy. And then there are a lot of other galaxies nearby. In a period of maybe 100 billion years or so, those galaxies will collide together and we'll have one big meta-galaxy in our local region. But because the energy of empty space, if it continues to exist, is causing space to accelerate, the expansion of space to accelerate, distant objects are moving away from us faster and faster. And eventually they'll be receding from us faster than light. Because they can't travel through space faster than light, but the space between us and them can expand that way. And as I worked out, in somewhere between 2 and 10 trillion years, if the current energy of empty space remains what it is, then all of the galaxies that exist outside of our local cluster, which is bound, will disappear. And in 10 trillion years, or 2 trillion years, let's say, where there'll still be stars, and you might imagine some civilization would develop, even one that isn't created by a simulation, will develop around its nearby star, and they'll have astronomers and other things. The universe will look to them like our universe looked to us 100 years ago, when we thought our Milky Way galaxy was it, and the universe was static and eternal. So in principle, that's what it looked like. I suspect smart scientists will figure out a way to figure out that it's actually expanding. But anyway, but that's okay. Even that's only finite in time, though, because eventually all the stars will burn out, collapse to form a big black hole in the center of our galaxy, which will then, if Stephen Hawking is right, over an indeterminately long time, 10 to the 60 years or something, will radiate away and disappear, and the universe will become cold, dark, and empty, and that's the future. That's the best possible future. The alternative is the expansion could stop somehow and we're wrong, and dark energy could go away, and it could begin to collapse, and then we'd be, in a shorter time, we'd have a reverse of the Big Bang, a big crunch, which would destroy everything. Yeah. Okay. Sorry to disappoint you.
Your friend Cormac McCarthy had once said that I'm a pessimist, but that's no reason to be gloomy.
That's right.
Professor, I'm an optimist.
Do I look like I'm not smiling?
I'm an optimist, but the picture you've painted only gives me reasons to be gloomy.
No, I think it's actually, I don't think it's pessimistic at all. It should make you feel even better by being around right now. How lucky are you? How lucky am I? How lucky are we to be around right now? We can ask these questions. And since, what happens 2 trillion years from now is not going to have any impact on your life now. So enjoy it while you can.
And I guess that is an uplifting way to think about it. I think T.S. Eliot had said it best, like, this is the way the world ends, not with a bang, but with a whimper.
Yeah. That's I've used that quote. I have to pay his estate to use it in one of my books. But yeah, absolutely. The way we now think is the universe is going to end with one big whimper. And
okay.
And it's, as I like to say, the future is miserable.
Yeah, what an uplifting thought. Okay.
It's exactly uplifting because we live in the present.
I feel so lucky. Okay, let's start wrapping up. And
I'm glad I've improved your outlook already.
Yeah, I feel I'm going to be bouncing on my heels as I walk around.
Exactly, I figured.
Yeah, let's start wrapping up and move into a final closing 5 questions. And I'm aware I did park aside 2 questions. We will cover them. Okay. First, let's talk about your influences. So what are some books, movies, role models that have strongly influenced you in your life?
Oh, lots. My goodness. Well, physics books, I've already written it. Well, Sir James Jeans did. Albert Einstein's books influenced me a lot, and Richard Feynman's books, among the scientists when I was in my formative years. Before that, there was actually a book, which I have somewhere on my shelf still. I think I got it when I was 11 years old, called Galileo and the Magic something or other. Anyways, about Galileo, and it certainly influenced me. Galileo became a historic figure in my mind, not just a historic figure, a heroic figure, and I thought of scientists as heroes. It took me a long time to overcome that, but it made me want to be a scientist, I think. So that, and then there's other books about humanity and how life is really ridiculous. Well, Albert Camus, the L'Étranger was a big influence to me when I became, an existentialist, I guess, when I was in high school. And also at the same time, even before that, Joseph Heller's book, Catch-22, which illustrated the ridiculousness of life, and Waiting for Godot, Beckett's book. I've always thought life is ridiculous, and those books helped confirm that, but in a fun way. Well, at least Catch-22 sort of, and not Camus' book, but it made me realize a lot of things. So those were very influential to me, I think. I used to read Greek history. I mean, history books have had a big influence. I like to do history. I suspect that's why I have so many books, and I have too many books, but because they've all had an influence on me. And lots of, and I love to watch movies and television. I watched TV incessantly when I was a child. I didn't start my homework till all the TV stations ended at 1 a.m. Even when I was 9 or 10.
Yeah.
And so I seemed to survive that. I found it very useful. I learned a lot of popular culture. So I'm not as opposed to, that sort of thing, because I think there's a lot of aspects of culture that people need to expose themselves to. The great thing is that everything has influenced me. That's why I find life so exciting. It's not just physics, it's history. Open your eyes, people. Everything is if you think about it, is amazing, and that's true for every aspect of the human experience. And it's why, as an individual as well as a scientist, but why as an individual, I try to open myself up to as many of those experiences as I can that will help, me experience what it means to be alive.
I think that's a fantastic list. We had parked aside a question about mysteries. You have written a book, The Edge of Knowledge, in which you explore some of the unsolved mysteries in the universe. Let's assume there's a genie here today that can grant you one wish. You can get an answer to a question that's been lingering in your mind for years. What is that one question you would like to get the answer to?
I could answer that facetiously, Everett. There's lots of ways to trick genies, but I won't do that one. I will say that I think the question Einstein asked is certainly one of the ones I'd like answered. Did the non-God have any choice in the creation of the universe? Namely, is there a unique set of laws of physics, or are we just an accident? I think that profoundly, at a deep level, is probably the most interesting question.
Do you have a hunch on the answer?
My hunch is I think the best evidence we have now is yeah, I told you. I think that unfortunately it's just an accident. But I'd like it to be the opposite. But I've learned that what I like doesn't matter. I think that's probably the one question I'd like to know. Yeah. But yeah, actually the question I really like to know is how can I do what you can do to the genie?
All easy questions for the genie. I'm sure they'll have the answer ready to go. Okay, last two questions. What would you like your legacy to be?
Oh, I don't think of legacy. I try not to. Look, you write books as part of. I would like my books to live on and to influence young people. They already are. I'd like them to have some influence on the way people think. I'd like people to, it'd be nice if people recognize some of the things I did, but I don't really care. As my friend Woody Allen said once about, would you like to live forever? Do you want your legacy to live forever? He said no. Something like, I think that was the question. He said no. I want to live on forever in my apartment. But my legacy is not up to me, and I don't spend a lot of time worrying about it. I try and have an impact on the world. I've tried my whole life to have a positive impact on the world if I can, and our knowledge about the world. And if that lasts, that's great. And if it doesn't really matter because I won't be around to worry about it.
As someone who has read your books, I do think they have been a great influence. So for someone whose mother wanted them to become a doctor, and for someone who frequently got discouraged during the PhD, I'm glad you stuck around.
Okay, thanks. Yeah, all that. It's all of that's true. Yeah.
Final question, and let's address that one final question I had parked aside. In the book Slaughterhouse-Five, Kurt Vonnegut says the following words. That is a very earthling question to ask, Mr. Pilgrim. Why you? Why us, for that matter? Why anything? Because this moment simply is. Have you seen bugs trapped in amber? Well, here we are, Mr. Pilgrim, trapped in the amber of this moment. There is no why. I want to check with you whether there's a different answer. What is the meaning of life, Lawrence Krauss? Why are we here? Is there a why?
Well, first of all, I use that quote in my new book. I quoted the last part, trapped in the amber. I think why is a bad question. I think we've been conditioned to think why, but almost all the time we think why. It's really how. Why presumes purpose. When I ask why is your heart on the left-hand side of your body, I don't think most people would say, oh, well, there's some purpose. I mean, someone did put it there. Some people do, obviously, but what we really mean is why. How does the body work in a way that what are the biochemical processes that cause that to be? So almost all why questions are finally how questions, and even why why is there something rather than nothing? What I really think the important question is how is there something rather than nothing? So I think why is the eternal search for why and meaning is something that people have created as a crutch, and it's understandable. We want meaning. We evolutionarily we look for meaning because as we often say, the people who saw the leaves rustle in the savanna of Africa and didn't think there might be a lion behind it didn't get to reproduce. And so the people who look for the people who look for meaning seem to reproduce. So we're driven to look for meaning, and it's exciting. I mean, to look, but I really do think that it's misplaced to think of the meaning as why. I think we're really trying to figure out is how the universe works, and then we make our own meaning, and that's okay. So meaning is subjective, and I think we're all entitled to make our own meaning, and take our own meaning and do what we think is meaningful in our own lives. So the ultimate meaning of the world, for me, it may be different than you. I make my own meaning, and that's fine. I have no problem, but I don't have any illusions that my meaning is in any way significant beyond me. Nor do I think I'm significant in the cosmos, even though, some people might think I think that.
So there is no mind independent meaning out there. We've been channeling a lot of people today, but I think in your final answer, you have channeled the computer deep thought from Hitchhiker's Guide to the Galaxy, where you've just said 42. That's a wrong question to ask. Yeah. You said the problem is you never knew the right question to ask.
Yeah. Well, in fact, I think the right question is what makes coming up with the right questions is what makes being human worth being human. And science is just a part of it. But it's coming up with good questions that really matter. And that's why I think kids should be encouraged to come up with good questions. Parents should be encouraged to come up with good questions. And all of us should never be afraid of asking questions, which is one of the problems that's happening in society now. But that's another podcast.
Professor, if people want to connect with you, read some of your books, find out more about your work, where can they go? How can they find you?
Well, they can't find me, but they can find my books anywhere, Amazon or bookstores don't carry my books as much as they used to, but you can go into bookstores and ask for them. And of course you can look, I do unfortunately tweet or X or whatever the word is, and L Krauss one. LawrenceMKrauss.com we try and keep up to the events I'm doing and the books I've written and the things I write. But I have a Substack site, Critical Mass, where I publish a lot of things along with newspapers and other things. And of course, I run this foundation, which you mentioned. And the foundation, the originsproject.org, runs the podcast I run and runs public events and trips and is doing the kind of things that I think is interesting as it tries to bring people closer to the questions you're asking, connect science and culture in the 21st century. So you can look there and maybe come on one of our trips or come to one of our events or listen to the podcast. Lots of ways to find me.
A lot of ways to find you online and your work. Professor, thank you so much for a fantastic conversation.
It was great. I really enjoyed it. I genuinely enjoyed it. Thank you very, very much. It was really very pleasant and deep. So that's very good, which I don't say about every conversation I have.